All right, so this is the first of the sections where we are going to start tying infinite series with specific functions. And we call this particular brand of infinite series a power series. So let's see right away what a power series is. So basically, a power series is just an infinite series, but it has a variable x in it that's raised to the n. So when you write out its terms, it takes on this form. Now, the Cn here can be really any expression depending on n. And we can define an f of x to equal this series. The domain of f, in other words, the set of legal x values that you can plug in, would be essentially the x values for which this series is convergent. So as an example of a power series, we have this particular series here. Now, all the Cn's are defined to be 1, so this is going to be like 1 times x to the 0, which is 1, plus 1 times x to the 1, plus 1 times x squared, plus 1 times x cubed, etc. And we know that this series, which happens to be a geometric series, is convergent when the r value, which is in this case just x, is between -1 and 1. Okay, and while we're not quite there yet in the conversation, just to give you a sense of the fact that power series really do represent functions, we actually can take advantage of the fact that this particular one is a geometric series with an a value of 1 and an r value of x, and we can see that this series is the infinite power series for the function f of x equals 1 over 1 minus x. All right, what we have here is a graph of the function 1 over 1 minus x, and we have the partial sum of the series x to the n. Now, we have to make it a partial sum with capital N here rather than infinity because Desmos just isn't smart enough to add up an infinite number of things. If we turn that function on, we currently have just the horizontal line y equals 1. And that's because currently capital N is set to 0, which means this is simply the 0th term of the series, which is 1. However, if we move the n from 0 to 1, you can see now this is the n equals 0 and n equal 1 term, so that's 1 plus x, which is, of course, this line. And it conforms to the function a little bit better. It's, of course, the linearization. It's the tangent line through the y-intercept. If we look at the next partial sum, we now have 1 plus x squared, which is a quadratic. And again, you can see that the quadratic is conforming very well to the shape of the function 1 over 1 minus x, which is in red. Letting capital N equal 3, we now are looking at the polynomial 1 plus x squared plus x cubed, which again conforms even better to the original function, but it's a cubic approximation. And as we continue to let capital N take on greater and greater values, meaning we're getting more and more terms in our partial sum, we can see that we are producing a greater and greater approximation of the original function. Now, this is capped right here at 30. So this summation is little n equals 0 up to 30, which means it's 1 plus x squared plus blah, 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 all the way up to x to the 30. And you can see that indeed it is an exceptionally close approximation of the curve 1 over 1 minus x. However, this approximation is only good over the interval -1 to +1. And that's because we understand that the geometric series that this thing represents is only convergent when x is between -1 and +1. So we would refer to -1 to +1 as the interval of convergence for this power series. And what we're doing today in 11.8 is basically going to look at various power series and determine exactly what their intervals of convergence are. Because the interval of convergence tells us exactly where that series behaves like a function. Okay, so before we get into intervals of convergence properly, let's quickly generalize our definition of a power series. Okay, so a power series centered at A is just a power series with, instead of x to the n, it's got x minus a to the n. So in the previous examples right here, these are power series centered at A. It's just in these cases, A is equal to 0. So for instance, this guy here is just 1 plus x minus 0 plus x minus 0 squared plus x minus 0 cubed plus da-da-doot. Okay, let's get into an example. All right, so here we have a power series, and we can see that it's centered at 5, and this is not a geometric series, because in a geometric series, the only place where n occurs is within an exponent, and here we have an n that's outside an exponent. It's just sitting here by itself in the denominator. So that rules out any chance of this being a geometric series. So typically, when we're asked to find the x values for which a series is convergent, in other words, we're looking for the interval of convergence, we will start with the ratio test. So yeah, let's do that. Okay, so an plus 1 is all of this stuff with n replaced by n plus 1, of course, and then multiplied by the reciprocal of an, which would be this thing. And now we'll line everything up with its friend. And as usual, we can collapse the absolute values around just the factor that involves x, because the n's are all going to be positive. All right, the limit is of n, remember, not of x, so only this part right here contributes to the actual limit being evaluated, and this is going to give us 1 times absolute value x minus 5. All right, so this is what we get doing the limit evaluation in the ratio test. Now, remember, we're looking for what values of x make the series convergent. So the way we determine the values of x for which the series is convergent is by kind of assuming that the ratio test is successful, meaning we're going to assume that this result here, which is the result of the limit of the ratio test, is going to be less than 1. We're going to make that assumption, and then we're going to see what restrictions that imposes on x in order for this reality to be true. So we're setting that quantity to be less than 1 because that's the outcome for which we could conclude that the series is convergent from the ratio test. Well, this part's always going to play out the same way. We have an absolute value of stuff being less than 1. So that means we can just write -1 is less than the stuff is less than 1 and isolate x in the middle. So of course we'll do that by adding 5 to all three parts here. So -1 plus 5 is 4. Then we get x in the middle. 1 plus 5 is 6. So preliminarily, our interval of convergence is the interval from 4 to 6. However, we actually don't know what happens when x is literally equal to 4 or x is literally equal to 6. In the ratio test, if x is 4 or x is 6, that's exactly the situation where the ratio test would evaluate to 1, which means we don't know whether the series converges at those endpoints. So it's premature here to actually put parentheses around the 4 and the 6. So let's rewrite it as 4 and 6, but we don't know whether there are parentheses or brackets around the 4 and the 6. It could be all parentheses or all brackets or even a mixture. Parenthesis on one side and bracket on the other side. So this means we have to handle the cases independently. Okay, so what does that mean? Well, it means we're going to let x equal 4 and see what our series looks like. So when x is equal to 4, we get 4 minus 5, which is negative 1. So this is negative 1 to the n over n. Now, what is the behavior of that series? Well, we can't use the ratio test on it because we know the ratio test is inconclusive, but hey, I mean, that's an easy alternating series test. So the Bn, which in this case is 1 over n, is clearly decreasing, and the limit of the Bn is equal to 0. So we can conclude that this series here is convergent. Okay, so this tells us that the series converges at 4. Okay, well now we need to do the same thing but with x equaling 6. So when x is equal to 6, we get 6 minus 5, which is 1 to the n over n. Yeah, except that 1 to anything is 1, so this is just 1 over n, right? That's, I mean, literally the divergent harmonic series, right? So this means the power series diverges when x is equal to 6. Okay, so we now know what the behavior is at the endpoints of our interval of convergence. So to answer the original question, which was for what x values does this power series converge, we can say that this power series converges when x is, you could write between 4 and 6 and including 4 but not including 6, or you could just use interval notation when x is an element of the interval from 4 to 6. And notice the bracket and the parenthesis indicating which endpoints are included or not included. Okay, again for context, I think we should pop over to Desmos and just kind of see what this looks like. At the moment, you have no real good reason to believe me when I say that this is actually the power series for the function negative ln of 6 minus x. But let's go and put them on Desmos and see what things look like. Okay, so here is the graph of y equals negative ln of 6 minus x. And let's turn on the series approximation. Again, we have capital N set to equal to 1, so this is literally just the first term of this series, which you can see gives the linear approximation of the function right at 5. As we make n change from 1 to 2, we now have a quadratic approximation, and again, contact is made with the original function right at 5. With n equal 3, we have a cubic approximation. And as we increase the capital N value, we get more and more partial sums in our series, and we're getting closer and closer conformance to the actual function. So this should at least give some justification to the claim that this series represents that function. Notice that, once again, the power series seems to conform to the shape of the function only between 4 and 6. No matter how many terms of our partial sum we calculate, we are never going to get the blue curve gluing itself to the red curve to the left of x equals 4. So at no point will this thing be a good approximation of this natural log function at, say, x equals 3.9, because this is a divergent series at x equals 3.9, as we know. Now let's notice one more thing. This series, we can see by its form, is centered at x equals 5. That center is always going to be the center point of the interval of convergence. So our interval of convergence in this case ran from 4 to 6. And what's right in the middle between 4 and 6? 5. The power series will always make contact with the function it's representing at the center, right at 5. And then it will extend as far as it can, equally in both directions, until one side hits a singularity, meaning some sort of discontinuous or non-differentiable or otherwise some sort of bad behavior on either side. And here, we of course have an asymptote at x equals 6 in the original logarithm function. So our interval of convergence extends outward from 5, both directions, until we get to this bad point 6, and then it stops, and it stops in both directions. So it's always symmetric about the center. And understanding the locations of the singularities of a function will allow you to predict the interval of convergence. This distance here, which is the distance from the center to either edge, so 1 unit in this direction or 1 unit in that direction, is referred to as the radius of convergence. And every power series will have a radius of convergence. It's just half of the measure of the interval of convergence. Okay, let's go and define these things. Okay, so the interval of convergence, which I often abbreviate IOC, is the interval of x values for which the power series is convergent. And the radius of convergence, which I often abbreviate ROC, is half the measure, meaning the length, of the interval of convergence. Okay, and finally, we should note, as pointed out, that a power series that's centered at A has an interval of convergence centered at A. Okay, for the remainder of this lecture, we're going to be looking at various power series and determining both their interval of convergence and radius of convergence. All right, so here we have a power series, and of course we want to know the interval of convergence and the radius of convergence. So while it's not strictly necessary to know this in order to answer the question, can we look at this series and actually determine where it's centered? Because a series is centered at A when the power series is of the form x minus a to the n. So the A is not quite obvious here, but if we factor the 2, we can see that this numerator can be written as 2 to the n times x minus 1/2 to the n. And in this way, we can see that actually the center is positive 1/2, which means whatever we get for an interval of convergence, positive 1/2 should be the number in the exact middle of that interval. Okay, to actually find the IOC, we're going to, of course, apply the ratio test. So that would be all of this stuff with n replaced by n plus 1 and multiplied by the reciprocal of an, so that would be just this. Okay, and let's line everything up with its friend. So for instance, we have 5 to the n over 5 to the n plus 1, rad n over rad n plus 1, and this thing over that thing. So by lining things up with their friends, we can see exactly what's going to cancel, what isn't, and we can also see that the absolute values are going to collapse around just the 2x minus 1 part. So here we get 1/5. No cancellation in the radicals, that's all right. And then absolute value of 2x minus 1. So again, let's remember this is a limit of n, not of x. So only this particular factor here will bear on the limit, and this factor evaluates to 1, which means the entire limit expression evaluates to 1/5 times absolute 2x minus 1. Okay, so we're now going to solve the inequality, this thing less than 1, in order to find exactly what the interval of x values are that makes the ratio test evaluate to a ratio of less than 1. Right? So that's going to give us almost all of our interval of convergence. We would just have to check the endpoints manually at that point. So, okay, very good. Let's multiply by 5 just to get the absolute value part by itself. And now we have absolute value of stuff less than 5. We can write this, of course, as -5, less than that stuff, less than +5, and continue isolating x in the middle. So adding 1, we get this, and dividing by 2, we get, and this is going to be, like I said, most of our interval of convergence, right? So the interval of convergence is the interval from -2 to 3, where we don't know if those are brackets or parentheses. However, we could calculate our radius of convergence right now, because the radius of convergence is just half the measure of the interval. So that would be like b minus a over 2. So b minus a over 2, which would be 5/2. So that's the radius of this interval of convergence. It's the distance from the center to either edge. And we predicted the center to be 1/2 at the start of this problem. And yes, 1/2 is the midpoint of these two numbers. And 1/2 is 5/2 away from -2, and 1/2 is 5/2 away from +3. Very good. So the last thing, of course, we need to do is set x equal to each of these endpoints, -2 and 3, and check the original series for convergence at those values. So when x is equal to -2, we get -5 to the n over 5 to the n rad n, and -5 to the n over 5 to the n is just -1 to the n over rad n. So we're just checking to see if this is a convergent series, which hopefully you can look at it and within a few seconds determine that indeed it is a convergent series. And we can dispatch it very quickly with the alternating series test. So our Bn, which is this quantity here, is decreasing, and the limit of that quantity is quite clearly 0. So that means that this is a convergent series, which means -2 is included in the interval of convergence. Okay, let's check x equal 3, the other endpoint. So 2 times 3 minus 1 is +5. This time we have the series 1 over rad n, because the 5 to the n's canceled. Oh, that's a p-series. Indeed, this is divergent, because p is equal to 1/2, and 1/2 is less than or equal to 1. So that means that 3 is not included in the interval of convergence. Okay, for the last two examples, it is true that one of the endpoints was included and the other one was not included. That's not always going to be the case, so you do need to check each one. It could be that neither one is included, as would be the case for any pure geometric series, actually. And it could be the case that both ends are included, so you just need to check them. So our interval of convergence is the interval from -2 to 3, including -2, not including 3. And let's quickly reiterate our radius of convergence, which we earlier calculated to be 5/2. So, hooray! All right, here we have yet another power series, and we're interested in finding the interval of convergence and the radius of convergence. So, yeah, let's go into the ratio test.
As of course is tradition.
So what do we have? We have -1 to the n plus 1 x times 2 to the n plus 1 over 2n plus 1 factorial, and this is multiplied by the reciprocal of an. Okay, so now let's just line everything up with its friend. So, strictly speaking, we can throw away these -1s because we're within an absolute value. But let's line them up. We can see that this is going to cancel down to just a single -1, and then that'll be annulled by the absolute value. Then it looks like we will have a mighty factorial battle to resolve here in a minute. And we also have x to the 2n plus 2 over x to the 2n. Okay, so the absolute values will collapse around simply the x's. The, of course, -1s, we can throw those away. So let's once and for all resolve this epic factorial battle. Okay, and we can see that the absolute values close around the x squared. However, as it happens, x squared is naturally never a negative quantity, which means that in this particular case, we don't even need the absolute values at all. We can just say x squared. So if we clean up the limit, we're going to get 1 over 2n plus 2, 2n plus 1 times x squared. Okay, well, remember this is a limit of n, not of x, so only this part of the expression will contribute to the limit. And of course this approaches 0. 0 times x squared is 0 no matter what the value of x is. So this evaluates to 0. Now this particular limit evaluated to 0 regardless of the value of x. And 0 is less than 1. So no matter what the value of x is, if we apply a ratio test, we're going to get 0, and 0 is less than 1. So that means that the series converges for all values of x. So our interval of convergence, we can say right away, is simply -infinity to +infinity. That's pretty much the best case scenario for a power series. And in this situation, we would simply say that the radius of convergence is infinity, because technically that's half the length of this interval. Okay, so you're going to get an IOC of all real numbers whenever the power series that you're working with represents a function that doesn't have any natural singularities or bad behavior. And this particular power series right here actually represents the cosine function. In fact, it's literally equal to the cosine function, and in many contexts, it's taken to be the actual definition of cosine of x. Let's go back over to Desmos and just see this. All right, so here's the graph of y equal cosine of x that we know and love. And let's turn on this particular power series. So at the moment, this is simply the 0th partial sum, so it's just the line y equals 1. It's the first term of this power series, which is a terrible approximation of the cosine function. But as soon as we let n equal 1, we now have a better approximation, although only near the center. And as we continue to increase our n, we get higher and higher degree polynomials, and you can see that this is taking on the shape of cosine. This is simply the n equals 6 case, and already that middle looks very, very cosine-y. So let's just go all the way to like n equal 30. Look at this thing as it conforms to the shape of cosine. And there's no right and left-hand limit of it. It's just going to keep extending outward. Here we stop at 30 because that's as far as this thing wants to go. But if we kept going to infinity, this thing would just hug the cosine curve all the way from negative infinity to positive infinity, because there's an interval of convergence of negative infinity to positive infinity here. And that's because there's no singularities blocking the expansion of the interval of convergence here from the center. And here's another power series. Let's find its interval of convergence and radius of convergence. So of course, we'll use the ratio test. So an plus 1 would be this thing, and divided by an. Okay, because of the way this thing was set up, all the terms are naturally right above their friends. So we can do what we always do. We're going to collapse the absolute values around just the factor involving x, and we're going to cancel everything that can cancel. So here we're going to get 2 times the factorial battle is won by the n plus 1 factor, and we have absolute value of x plus 2. Okay, so we're taking the limit as n approaches infinity. So this is the only factor here with an n in it, so this guy wants to run off to infinity. Remember, x is just a constant, so x plus 2 is a constant. So one could quickly conclude that this limit must evaluate to infinity no matter what, except there is one x value for which this does not evaluate to infinity. And that is whatever makes this quantity equal to 0. So in other words, when x is equal to negative 2, then we have a quantity of 0 here, and this limit evaluates to 0 in that case. So to be clear, the result of this limit depends on the value of x. The result is 0 if x is equal to negative 2. But if x is any other number besides negative 2, then we have some positive number here times a limit that's approaching infinity, which evaluates to infinity. All right, so in terms of the ratio test, and the context being we're looking for where this is a convergent series, what does this mean? Well, infinity is, of course, greater than or equal to 1, and 0 is, of course, strictly less than 1, which means that according to the ratio test, this series is convergent only if x is equal to negative 2. Okay, so how do we write down our interval of convergence? Well, it's the interval containing exactly negative 2 and nothing else. So one way to write that would be the closed interval from negative 2 to negative 2. And you would need brackets, because if you had a parenthesis on either end or both ends, you're communicating that you're not including that endpoint. Now, although this is technically a correct way of writing it, it's pretty non-standard. So in a situation like this, we would use curly braces to indicate the singleton set containing the element negative 2. Okay, well, what's our radius of convergence? Well, that's the half of the length of this interval, which would be 0. So altogether, this power series is pretty useless. right? It converges only for a single point. So in practice, we wouldn't really care about it, but it is what it is.